We're live. Let me see if it's working on my desktop, and then I'm going to say hi and hello to everybody really properly in just 5 seconds. Ooh, I see it. I see the thing with the thing. Welcome everybody so much to this live, to yet another live stream episode of this channel, Baji the Handsome Cat. There, let me save that setting. And are we good? Is the live happening? Is the live living? Are we good? Can you hear me? Can you see me? Okay, so let me get started. Okay, welcome, 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 welcome to yet another amazing episode of this live stream episode making channel Baji the Handsome Cat, where we cover cats and physics. And most importantly, pretty much we show the kitty cats doing their regular lifestyle, their hangouts, and we chit chat, we get together, we catch up almost every day during our lives. There's something in my eye. I'm so sorry. See, the fun thing about a live stream is that there's no cuts, no pauses. It is what it is. You get me in the flesh. You know, whatever you see is whatever is happening and whatnot. And we discuss physics, astronomy, astrophysics, and cosmology during these lives as well. During these nighttime or evening lives, we have been having lots of fun catching up, as well as covering these extremely exciting topics that fall under physics, cosmology, astronomy, and astrophysics, which happen to be my area. So along with the kitty cats on this channel, you can also expect to get some physics classes, some physics lectures, if you will, some lessons to do with physics. And sometimes we are interrupted by extremely cute members of this channel, cute kitty cats indeed, who also join and who also may or may not be partaking in the physics. So that's what really happens. And then today, believe you me, I want to talk to you about a very exciting update indeed. This has to do with our friendly neighboring galaxy Andromeda and the fact that there is a new paper that has come out that came into my attention, which says that the merger that we were supposed to have between our galaxy, the Milky Way galaxy, and Andromeda may not be such a certainty after all. So this is some exciting, very not controversial in the sense of, the science is saying what it is, but this is some real hot tea that has come out in astronomy, in the world of astronomy, that we're going to cover tonight. Hello, Rehan. Assalamu alaikum. Wa alaikum salam. So let me share the live before I forget, and then we will keep on keeping on. And we will also share from the book called Atom by Dr. Lawrence Krauss, because there is something else, another very important topic that we will also be talking about. So that is what the lesson today will be about. Hello, Rehan. Says Eid Mubarak. Hello everybody. Thank you so much for joining. If you're joining, thank you so much for being here. If you're watching this as a live replay or video upload later on, also thank you so much. And please do leave your comments. Can't wait to see them when I wake up. And as always, it's very exciting to hear and see everything that everybody has to say. Put your comments in the chat as you're in the live. Enjoy, sit back, relax, enjoy the live, enjoy the information. And hello, Akwasi. How are you? Thank you for those laughing emojis. I'm not sure exactly what you're laughing at, but keep it going. And also everybody else, thank you so much. Ooh, and please do like the live. Can we get 20 likes? Could you please double tap the screen and give us some likes? Thank you so much. Let me share the live. That is always one other thing that I forget before I get it going, get it started. So I remember when we were heavily discussing a lot of the astronomy types of. Junior Donald Kaya says, watching you from the Pacific Ocean. Oh my gosh, how is the Pacific? It's my favorite ocean. It is so very big and it is most of this earth. So thank you so much for being here from the Pacific. How is it? Is it choppy today? Is it very blue? Is it dark blue? Tell us more. And I will tell the channel that we are live. So Sorry, give me one more second. It takes me a little bit. Okay, thank you so very much, everybody, for being here. Good evening, good night, good morning, good afternoon to all my continents. Africa, you go first. Africa, if anybody is here from Africa, put a pink heart in the chat and we will say hi to you. Thank you so much and welcome to Africa. Welcome to Asia. Welcome to Europe. Welcome to North America, South America, Antarctica, Australasia, Australia, the country as well as the continent that includes New Zealand. Welcome, New Zealand. Welcome, Madagascar. Welcome, welcome, Hawaii. Welcome, all the islands, all of the continents, everybody. If you're from a specific location that you would like to share with us, please put it in the chat and we will say hi to you. We will say hello to you. And if you have any other general comments, thoughts, questions about physics, astronomy, astrophysics, kitty cats, cosmology, then put it in the chat as well. And I may use the first 20 to 30 minutes of this live stream to kind of cover the topic that I'm going to cover tonight in some detail, sort of keep on going for the first 20, 30 minutes without too much interruption. So I might just read your comments in about 30 minutes at the 30-minute-ish mark on the live stream timer. Okay, so just thank you so much for your patience. Still go ahead and put anything in the chat that you want and hang out and chit chat with each other. And I will read your comments in just a second. Tonight, I want to tell you about this extremely exciting news. This paper came out that I have up here on my laptop with me, actually. It is published in Nature Astronomy, and I've actually put a link in the description of this live stream, hopefully, which you can see in the in this description about this paper. So you can even link to it, you can go to it and read it yourself. But basically, what I would like to share is remember how, if we have been coming to these lives for a while, remember how in the past we have talked about this very exciting merger between our galaxy, the Milky Way, and Andromeda, our friendly neighborhood galaxy as well. So both our galaxy, that is the Milky Way, and Andromeda is our neighboring galaxy, are both spiral galaxies. Now, if you remember also that we actually classified galaxies with the help of Hubble. Hubble in the past has given us a way to classify galaxies based on their shape. So these shapes are spiral, elliptical, and irregular. So our galaxy is a very beautiful, very wholesome, very big, very filled with all kinds of things kind of galaxy. I can tell you more about how our galaxy is such a wholesome galaxy, and I mean wholesome in the sense that it's not a very specific or weird kind of galaxy, which has only specific weird things going on, but it is sort of a more wholesome galaxy. And I can dive into that more in another live or later on in this same live. But basically, our galaxy is a very wholesome galaxy. It's a spiral galaxy. And it's very beautiful, very beautiful, has lots of stars, lots of things going on, lots of variety, actually has a big halo, which has dark matter, things like that. And we have a neighboring galaxy in the local group. So sometimes galaxies is a way of course, organizing matter in this universe, but sometimes even galaxies or some few other galaxies that are nearby are grouped together in a cluster, and that cluster is given a name. So in our sort of local cluster, sometimes called the local group, there is another spiral galaxy. It's our neighbor galaxy, and it is called Andromeda. Very beautiful name. I actually know somebody called Andromeda. I believe it was somebody's daughter. They were in astronomy themselves, and they named their daughter Andromeda. Very beautiful. But this Andromeda galaxy and us, we basically thought for the longest time, it might even be something like 100 years. I could be wrong, so double check that. And it might be better printed in the paper as well. I think for about 100 years, we have thought that us, our Milky Way galaxy and Andromeda, are going to merge together, and it's a sure shot merger. Like we thought it was a very high probability that Andromeda and us will merge. And what is more, Andromeda and us are both spiral-shaped galaxies, and so we also knew that once these two spirals merge, this will become an elliptical galaxy. The resulting galaxy will have an elliptical shape, and I was quite sad about that because I like our spiral shape, and I have a certain, I guess, attachment to the spiral shape of our galaxy, even though this was not going to happen for another 5 billion years or so, where Andromeda and us would be properly merged. is what we thought would happen, is that we would merge. This wasn't going to happen for another 5 billion years, and that is billion with a B for boy, B for Baskin Robbins, B for billion. So in about 5 billion years, we were supposed to do this merger. And I was sad at today's date because I was like, well, Andromeda is a galaxy that is a spiral shaped galaxy. We are a galaxy that is a spiral shaped galaxy. And as you know, in any kind of process in the universe, the entropy of something always increases. The entropy of the universe always increases. That is the second law of thermodynamics. So as you might guess from that, is that when these two spiral galaxies merge, they were not going to stay spiral. So the spiral shape is actually a more orderly state than is an elliptical shape. So once these galaxies had merged, these would become an elliptical shaped galaxy. Give me 1 second. Can I? Sorry. Yeah. Hopefully that's all good. Can everybody see me and hear me just fine? So anyways, I actually thought that was going to be a little sad if us, Milky Way galaxy, and Andromeda spiral galaxy merged to become an elliptical galaxy, because I think our spiral shape is just beautiful. So anyway, turns out with recent data and recent research and work and all of that stuff, that actually it is not so certain anymore that we will do this merger. It is not so certain anymore. Indeed, it is apparently about a 50-50 chance that us and Andromeda will merge, which is quite dramatic. This is hot topic news, guys. I hope you're listening with your ears cleared. This is really hot tea in astronomy. We thought that we were going to merge with Andromeda for sure. But turns out that we, as in Milky Way and Andromeda, might just decide to love from a distance and not merge together to form an elliptical, in my opinion, worse shaped galaxy. But we might just stay away from each other and love from a distance, let our gravitation do its thing, but not totally merge. Now, of course, we will eat and cannibalize other smaller galaxies like the Large Magellanic Cloud, most likely, probably for sure, because there's other things in the local group that we can still eat as the Milky Way galaxy. So, just like in the food chain with animals, bigger things sometimes eat smaller things. In galaxies too, sometimes bigger galaxies will kind of eat their smaller neighbors. So for us, for instance, the Large Magellanic Cloud, the Small Magellanic, there are other irregular galaxies kind of nearby that we might end up cannibalizing and sort of swallowing whole. And the thought was that Andromeda coming towards us is going to be that way. But turns out now there is a 50-50 chance only. So 50% chance that we may merge with Andromeda and 50% chance that we may not merge with Andromeda, which is really, again, that is so dramatic. And I'm going to read to you the abstract from the paper that has published on this topic, okay? So let's see. No certainty of a Milky Way Andromeda collision. Can you believe that? That is the name of this Nature paper. So by the way, Nature is a journal. It may cost money to read this paper, but the way I am seeing it with this link, I can sort of read it. So hopefully you can too, and I've linked to this in the description of this live stream video. But basically, again, this is in Nature Astronomy, and the title is No Certainty of a Milky Way Andromeda collision, because if something is going to happen as a 50-50 chance, we can't say, oh, that is certain. That is most uncertain, if you will. So anyway, get ready for the abstract. It is commonly believed that our own Milky Way is on a collision course with the neighboring Andromeda galaxy as a result of their merger predicted in about 5 billion years. The two large spiral galaxies that define the present local group would form a new elliptical galaxy. Here, we consider the latest and most accurate observations by the Gaia and the Hubble Space Telescopes. Oh, love it, Hubble, along with recent consensus on mass estimates to derive possible future scenarios and identify the main sources of uncertainty in the evolution of the local group over the next 10 billion years. The local group is basically the name of our neighborhood. The neighborhood of our galaxies is called the local group, kind of like if you're in a neighborhood, I don't know, some neighborhood, that neighborhood has a name, depending on where you are. Our neighborhood in terms of galaxies is called the local group, okay? So us and Andromeda and the Large Magellanic Cloud and other lesser beings, if you will, because I think our galaxy is so important and so cool. Well, the local group is the name of our neighborhood. So, anyways, they identified the main sources of uncertainty in the evolution of the local group over the next 10 billion years. So that's a long time, 10 billion years. We found that the next most massive local group member galaxies, named the M33, so that's another galaxy, and the Large Magellanic Cloud, distinctly and radically affect the Milky Way Andromeda orbit. So guess what? These other things, M33 and Large Magellanic Cloud, these other galaxies are actually going to have a bigger impact on our collision with Andromeda than previously thought. Although including M33 increases the merger probability, the orbit of the Large Magellanic Cloud runs perpendicular to the Milky Way Andromeda orbit and makes their merger less probable. Less probable. Wow, wow, wow. So if you're for this merger, then you can blame the Large Magellanic Cloud. If you are against this merger, then you can thank the Large Magellanic Cloud and its perpendicular orbit to the merger of our galaxy with Andromeda. Large Magellanic Cloud is kind of coming in the way, if you will, and there's other masses to account for. And because of this, the more accurate estimate is that we will not, or we might 50-50 like merge with Andromeda, not a sure shot merger in the full system, where we of course include M33, like this person is saying, or these people are saying. M33 is another galaxy. Large Magellanic Cloud is another galaxy, of course. We know about the Large Magellanic Cloud, is mentioned a lot. It's an irregularly shaped galaxy, which we will most likely, for sure, probably cannibalize us, Milky Way. So in the full system, we found that uncertainties in the present positions, motions, and masses of all galaxies leave room for drastically different outcomes and a probability of close to 50% that there will be no Milky Way Andromeda merger during the next 10 billion years. Based on the best available data, the fate of our galaxy is still completely open, guys, completely open. We're going to be so single, guys, so single. We will be isolated, lonely, successful, and single as the Milky Way galaxy. We will not be merging with our friendly neighborhood galaxy, Andromeda, as in 50-50 chance that we might, but 50-50 chance that we will not. And we will be so single, guys. So, the local group. I'm going to read a little bit about the paper as well, okay? Thank you, everybody, for being here, by the way. Thank you so much. This is an exciting night, a very exciting night. Thank you so much for liking the live. Can we get 20 likes? Can we get 30 likes? I will read a little bit of the main body of the paper as well here for you, because this is just so wonderful. The local group contains two large spiral galaxies, us, Milky Way, and the Andromeda galaxy. By the way, the Andromeda galaxy is sometimes called M31, along with approximately 100 known smaller galaxies. 100 known smaller galaxies. So the local group, once again, it is our Milky Way and the Andromeda, which is another spiral galaxy, also called M31 sometimes. And then there's approximately 100 other smaller galaxies that are all part of this local, like this is the local cluster, if you will, okay? So in addition, it probably hosts other galaxies yet to be discovered. So the other thing is that we don't always know about everything. Even our local group is quite spread out, right? Even just our galaxy is 100,000 light years across. That is just our own Milky Way galaxy is 100,000 light years across. So as you might know, the space is very sparse. Everything is very far away. Even when they're part of the local group or the local neighborhood, things are actually very, very far away. So it's extremely possible that there is things that we haven't discovered yet. And by the way, once those things are discovered, if they're discovered at any point, then that might again change the calculation, if you know what I'm saying, so that could happen too. So, but let's read what this paper has to say, which I'm very excited for this paper. I mean, they're in Nature, so congratulations, by the way, to these authors. I will read their names in just a second. So anyways, in addition, it probably hosts other galaxies yet to be discovered, and according to the standard cosmological model, a vast number of completely dark substructures, so dark matter. The negative radial velocity of M31 towards the Milky Way has been known for over a century. So, for over a century, we have known that our friendly neighborhood galaxy Andromeda is kind of coming towards us. For over a century. What did I tell you a little while ago? That it might be 100 years that we've known this. 100 years, even before its distance was first accurately measured, even before we knew how far away Andromeda really was from us, we kind of knew that it's coming towards us. Hello, it's coming towards us. But it's going to not merge with us, maybe because of large Magellanic Clouds interference. Okay? However, although indirect methods have since been used to constrain the transverse components of M31's velocity vector, direct measurements of the minute proper motions have been achieved only much more recently with the Hubble Space Telescope. Only recently. The first numerical studies of a possible Milky Way M31, which is Andromeda, merger predate even the early estimates of the transverse velocity. The finding that the Milky Way M31 motion is close to radial immediately led to the prediction of a probable future collision and merger. This scenario has since become the prevalent narrative and textbook knowledge. So that's what I mean, is that this is textbook knowledge that we will merge. Oh my God, I have to see. Excuse me. Hello, everybody. Oh my gosh, I had to sneeze. It's the spring allergies. Hi, Casio. Hi. Hi, Casio. Hi, Stephen. Hi, Reese. Hi, everybody. I'm going to say hi to everyone in just a second. So, the big deal thing here is that, see, astronomy is always evolving. It was considered a prevalent narrative and a textbook knowledge. Remember, we even read it from a textbook. Actually, turns out we read it from the Foundations of Astrophysics textbook earlier that we were going to merge with Andromeda, guys. We read this from a textbook because in classrooms and textbooks, this is what it was being taught, because it was considered to be very well-established knowledge that we will merge with Andromeda, but now the probability of that merger is only 50-50. So do go ahead and check out that paper that I have linked in the description of the video later on if you are interested in reading the full thing. Okay, now let me give credit to all the authors here. This paper is written by Till Sawala, Jehan Delhomel, Alice Deason, Carlos, Frank, Jenny, Hakkinen, Peter Johansson, Ate Kitanranta, Alexander Rawlings, and Ruby Wright. Congratulations to all of the authors, because it's a big deal to get published in Nature Astronomy. Congratulations indeed to everybody who's written the paper. Hello, Aroldo. Congratulations to everybody who's written the paper and who has been part of this excellent work, this very exciting update to the merger status. Okay, let me read a little bit longer and then we'll move on to the next topic, which has to do with matter and antimatter. Okay. And before that, I will say hi to everybody. What's the name of the one who's doing it live? So the name of this channel is Baji the Handsome Cat. We are a cats and physics channel. We cover astronomy, astrophysics, and cosmology during the live streams. And my name is Baji's mother, Baji the Handsome Cat. I am his mom. So, predicting the future of the local group. The Milky Way and M31 both contain remnants of past mergers and interactions with other galaxies. Predicting future mergers requires knowledge about the present coordinates, velocities, and masses of the systems partaking in the interaction. In addition to the gravitational force between galaxies, dynamical friction is the dominant process in the lead up to galactic mergers. Dynamical friction is the dominant process in the lead up to galactic mergers, as it transfers orbital kinetic energy to internal energy of the objects involved, and consequently leads to the decay of galactic orbits. Wow. Oh, wow. Transfers orbital kinetic energy to internal energy of the objects involved, and consequently leads to the decay of galactic orbits, guys. Goodness. In this study, we parameterized the density profile of each halo as a spherical Navarro-Frank White profile with an isotropic velocity distribution, and we used standard assumptions about their concentrations, C, and velocity dispersion profiles. We calculated the dynamical friction using an analytic formalism, although non-gravitational processes such as gas drag and star formation leading to increased central densities and so on. So star formation is, can also whether I know how much. So we've talked about this in the past, where star formation and where it happens in the galaxy is something we've covered in the past when we were covering a lot about galaxies a while ago. This was a few months ago. And we talked about various different galaxies, and even in our own galaxy, which are the star forming spots in our own galaxy, right? There's some parts, there's obviously a bunch of arms of our spiral galaxy, spiral shaped galaxy, some spiral arms, and there are star forming regions in our galaxy. Not every region is equally star forming, if you will. Okay, so this type of thing, the star formation process, can also lead to increased central densities and so on, also shape the final stages of a merger. The phase of the orbit that defines the occurrence of mergers is largely determined by gravity, which in turn is dominated by the dark matter component in the standard cosmological model. See, dark matter is so important in all of this. Thank you so much. Please do like and subscribe. Please do like and subscribe. Thank you. So, the rest of it is pretty technical looking, so I'm going to leave it to you to go read it if you are interested. I'll see if there's any more tidbits that we can share here. I can show you these pictures later on, but I think that is pretty darn interesting. Let me see if I can go to the discussion or the last bit to see if there's any powerful conclusions to be derived from this. Ooh, yes, the summary. I think the summary is good. So you will see that they will talk about some sources of the uncertainty and whatnot. Oh my gosh, everybody. Thank you for being here. Please do like and subscribe. Yes, I have been reading Stephen's book during the day lives. Sometimes I've read excerpts from his book. So that's been fun too. And we've been kind of doing a book vibe type of thing in some of the lives and discussing sort of the writing of the book and whatnot. Bye, love you. Good night to everybody who's leaving. But if you're staying, then thank you so much. And keep on keeping on. And I will do a goal. I'll do a goal for the live. I'll say like and subscribe. Thank you for being here. Thank you. Please do double tap and give us some likes. Give us some super chats. Give us some love. Okay. Even using the latest and most precise available observational data, the future evolution of the local group is uncertain. It is uncertain. Intriguingly, we found an almost equal probability for the widely publicized merger scenario, albeit with a later median time to merger, and one where the Milky Way and M31 survive unscathed. We reached this conclusion by including the LMC, Large Magellanic Cloud, and importantly, considering the relevant uncertainties in the observables. Our results are not sensitive to the necessary choices of gravitational softening, merger threshold, or dynamical friction scheme. We use n-body simulations to validate the procedure. For several examples, importantly, our results were obtained using methods very much like those previously used to predict the MW or the Milky Way M31 merger. And when we applied our methods to the same restricted initial conditions, we obtained very similar results, guys. Very similar, they say. So anyway, all of that is to say, my dear friends, that wow, wow, it's actually a 50-50 chance of the merger. I don't know why, but I think I'm happy about this. I didn't want us to merge. I didn't really want us to merge. I like our galaxy. I like its shape. I like it. I didn't want us to merge. Okay. Hi, Nathan. Let me say hi to everybody. Okay, there was some weird person saying the same thing way too many times. Hi, Pranay. How are you doing? Hi, Wonder Boy. Hi, Steven. Hi, Pranay again. Hi, Aman. Hi, Aman. Hello. Hi, Abul Fazl. Hi, Nathan. Hi. Hi, Aroldo. Hi, Kakit. Hi, Berang. Hi, Ishan. Ishan said nice earrings. Thank you. What's your name? Nathan, what's your name? Her name's Hufflepuff. I love that. Hi, everybody. Okay, everybody, thank you so much once again for being here. If you're just now joining, please do rewind and see the update of the century that we just gave about the Andromeda Milky Way merger and how it's not so certain after all. We may not merge with Andromeda after all. So please do see the whole live. Thank you so much. Yes, it would take 5 billion years, but what used to be considered a certainty collision is now being considered as a much less certain collision. And it's in fact like a 50% chance of not colliding. So that's the important update here. Hi, Abul Fazil. Hi, Acacio. Hi, Kalkid. Hi, Nathan. Nathan, how are you? Stephen, how are you? Stephen says, when I was in high school back in the 1980s, I had this same idea in a comic book form. I'm pretty sure you're the smartest person streaming right now. Thank you, K Hackett. 7, thank you so much. Thank you so much, K Hackett, Abul Fazil, Acacio, Stephen, everybody. How are you doing? How's everyone doing? Next, we will talk about matter and antimatter and how there might be some more probabilities of interest to us that tell us why there is more matter than antimatter and why indeed we ended up being here, because we would not be here if certain things had not gone a certain way. And in fact, if there was an equal amount of matter and antimatter which annihilated each other and only made radiation, then interesting things like you and me and atoms would not be forming. And so this is something we will talk about and read about and discuss in detail from the book called Atom by Professor Dr. Lawrence Krauss, which actually happens to be one of our favorite books and one of the favorite books that people have recommended or requested in this live. So get ready for this next topic going on next, okay? In the meantime, how is everyone doing, my loves? I'm great camping out in the tent at the lake. Oh, Cassius says buenas noches. Buenas noches. How are you? I have a question. Avoid. I'm not an anomaly. I think they have just taken into account more factors than they did before, and they have taken into account M33's contribution as well as the large Magellanic clouds. contribution to us merging or not merging. But there's a lot of different factors in the calculation which might not have been taken into account earlier, and also we're working with the more accurate data. And it's also that we had estimated this a while ago, and it was time to kind of probably confirm everything with the newest data. For the longest time, we thought it was a certainty, a sure shot certainty, but it's not so certain after all, is what we're finding with the new data. Okay. But I'm not sure about what you mean by an anomaly. That's why I wanted to ask. Yeah. So it's not that they found an anomaly. It's just that they have better numbers for everything, better data. They're taking into account more important parts of the local group, like the M33 galaxy and the Large Magellanic Cloud. It sounds like Large Magellanic Cloud is sort of the reason why we will not be doing this merger. The Large Magellanic Cloud's orbit is kind of preventing the merger. Because, see, everybody and their masses and their gravitations, including, of course, dark matter, is playing a role in the orbit of this collision, right? And so if there's other things that kind of pulling us in a different way, or putting this sort of collision, affecting the collision in a different way, then we will not be colliding. The small Magellanic Cloud, yeah. So I think the biggest things that they considered is M33 and Large Magellanic Cloud. Probably we should read the paper in more detail to see if the small Magellanic Cloud has an effect on this or not. I mean, to some extent, probably it does. Everything has an effect on everything, but I think some of the things might be sort of not part of the estimate, and some of the things might be deemed more important to include in the estimate, and they have updated those calculations with those estimates. Okay, so that's kind of what they've done here. How is everyone doing? So Nathan, you're camping. That's cool. Okay. So now that we have talked about the most exciting collision, which may not be happening after all because somebody ordered the cancellation of this collision, maybe 50% chance, we will now move on to another topic. This is going to be from the book called Atom by Dr. Lawrence Krauss. And he has talked about matter and antimatter in this next chapter that we're on. Okay. So let me pull this up from my other device. I have all kinds of devices here. And let me pull it up here. So basically, the thing is that in this chapter, so we have been covering this book, by the way, for a little while. We haven't gotten too far into it, but it is a sort of requested book on this channel. So hopefully, if you're joining, that you enjoy. And if you see this later on as a live replay or video upload, and if you were one of the ones who was interested in the book, please do leave a comment. I don't see my mod Chickpea here because he was one of the, people actually who requested the book. So Chickpea, if you're seeing this later on, please do like, share, subscribe, comment, and leave your comments to give us your thoughts and your support on this matter. I'm going to take some sips of my water, and then we will talk about matter and antimatter and some probabilities that may have led to more matter than antimatter, and sort of at which point did the universe decide that there was going to be more matter, which ultimately leads to things like us in the universe. Okay, so that's where we're going to be talking about next. So there's definitely, hello, hi, Crazy Sick Wine. There's definitely older galaxies, but they're not from the beginning of the universe, because the very beginning of the universe did not have any galaxies, okay? So I don't know, about 16 billion light years away. Something that would take light 16 billion years to travel. The universe is only about 14 or 15 billion years old. So I'm guessing what you're asking is have they found any galaxies that date back to the beginning of the universe? And the answer is that there were no galaxies at the very beginning of the universe. That one picture I showed the other day actually shows you what was kind of going on in the very beginning of the universe. And there was some other processes going on. It used to be a very radiation dominated universe. and whatnot. And then slowly we started to form. Actually, there was the cosmic microwave background radiation era, the recombination era, and then later on we started to make the first stars and galaxies. And true, we do have, if you're asking like, have we seen some really old stars, then yes, we have. We actually have seen some very metal poor stars, which is another way of saying we've seen some very old stars, because the oldest stars were mainly just hydrogen and helium. They were not metal rich, because to be metal rich, you'd have to go through those processes, live and die as a star, make the next generation of stars, and so on and so forth. So yes, we do have a number of metal poor stars that we have seen and are cataloged. Okay. Crazy says, if it isn't the marvelous tree, how art thou on this brilliant night? I am good. How are you? Did you like the live? Like, share, and subscribe. And yeah, put your comments in the chat. Yeah. So, I mean, again, if unless there is some other evidence about the age of the universe, so far we think it's around 14 or 15 billion years old. So, okay. Okay. So now, but as far as the metal poor stars go, absolutely we have some in our catalog. We don't have every one of them, I'm sure, but there is some even in our own galaxy. Actually, isn't it so crazy? We have some stars, I believe, in our halo that are quite old and much less rich in metal. Okay. Like we have some older stars in the halo of our own galaxy, which are more metal poor and they are older. Okay. We also have a ton of dark matter in our halo, which is a topic of active research. You cut off. Can you see my comments? I see this one, crazy sick one. Can everybody hear me and see me okay? I see the one where you said, well, and then I see Acacio, then I see Steven, then I see you again. Bad connection, says crazy sick one. Acacio says perfectly. Yay! Thank you for the feedback. Crazy sick wine, it might be your internet. Okay, let's now go on to the next topic, which is going to be this book. Whoops, I spilled. A simple accident often determines the difference between life and death. Whoa. This can occur in art, as in the 1999 film Sliding Doors, where the fact of missing a subway train changes the course of a young woman's future, or in real life, as when a friend of mine missed TWA Flight 800 to Paris on July 17, 1996, in order to visit his father in the hospital, and thus avoided incineration in the sky. Oh gosh, the events near the beginning of time that immediately preceded the birth of our atom may seem innocuous enough, but a slight alteration in the initial conditions and atoms and the cosmos as we know it would not exist today. So a slight alteration and we may not be here, okay? Crazy, the swearing type of messages actually get censored by YouTube, but thank you for being here. No worries. No worries. You can figure out your phone and we're still going to be here, okay? Just as fictional heroes from Shakespeare's Hamlet to Heller's Yossarian are subject to compelling historical forces often beyond their control, our inanimate hero is dependent upon the accidents and vicissitudes of cosmic history. When I speak of accidents, it may sound as if I've given up any pretense of scientific accuracy. In fact, however, predictable accidents are the basis of essentially all modern scientific inquiry. Remember how quantum mechanics is super probabilistic and there's uncertainty and all of this stuff? Accident is sort of another, we will see what he has to say about this, Lawrence Krauss. But accident is sort of this chance occurring type of thing that we might want to feel very comfortable with ever since quantum mechanics started being a thing. Okay. In fact, however, predictable accidents are the basis of essentially all modern scientific inquiry. In our laboratories today, we literally wait for accidents, except we stack the deck, creating favorable conditions according to which the laws of probability must play themselves out and we wait and watch. Sometimes this involves building mammoth tanks of water in deep mines. Remember the neutrino experiment that he has mentioned in chapter 1. Sometimes it involves building single machines larger and more complex than anything before created by humanity. In such machines, we recreate for a brief instant certain features of the early moments of the Big Bang. Located between the Jura Mountains to the north and Lake Geneva and the Alps to the south is the Geneva International Airport. If you're lucky, and the low cloud bank, which sometimes hides the valley, is absent, then just before landing there, you may glimpse a cluster of buildings less than a mile northwest of the airport. Like the tip of an iceberg, the central administration buildings of the European Laboratory for Particle Physics, or CERN, the French acronym for the original, now politically incorrect name, European Council for Nuclear Research, belie a far more impressive structure hidden below the surface. The picturesque farmland and small hamlets dotting the French-Swiss border do not betray any evidence of one of the largest tunnels in the world. Hello, the world listens. Thank you. Thank you, Marut. Thank you so much for the hearts. Thank you. Traveling 26 kilometers in a vast circle ranging from about 50 to over 100 meters below ground is the CERN Large Electron Positron, or LEP, Large Electron Positron, LEP Collider Ring. Soon to house a new machine, the Large Hadron Collider. This book is a little older, so the Large Hadron Collider might have been pending at this time of writing of this book by Professor Dr. Lawrence Krauss. And keep going with what you do. Thank you. To visit the CERN laboratory or any major particle accelerator facility today is to feel like Gulliver entering Brobdingang, the land of the giants. Every object seems out of scale with mere human dimensions. The LEP tunnel itself, for example, while 26 kilometers long, is wide enough to easily accommodate a modern sport utility vehicle or two, should it ever be turned into an underground racetrack. The tunnel is accessible from the surface at one of 4 different laboratory locations. At each site, one of 4 mammoth particle detectors can be found. Each is the size of an apartment building, built deep below ground, contained in experimental halls that could dwarf the stage at Radio City. Each behemoth is constructed from thousands of separate components fabricated by hundreds of physicists and technicians hailing from dozens of countries scattered across the globe. And each is built to a precision of fractions of a millimeter. By the way, this is what we have accomplished in this century. Somebody was asking the other day, what have we accomplished in the 21st century? Because the 20th century seems so rich, so insightful, so much going on. For example, relativity and quantum mechanics, the mammoths of that century that gave us such new, deeper broader, amazing insights into physics and nature. But what have we done in the 21st century? Have we gained a lot of big insights? Have we learned new physics? Sometimes where we might not have learned too much more or too much new physics, where we have really gone leaps and bounds and progressed a lot is actually in experiment and experimental observations and building amazing experiments with accuracy and precision like none other or never before. Okay, so this is exactly this description kind of actually sums up what it is that is so special about our current century, our current state of affairs. What do we do these days of that is worth mentioning? It's this type of thing. These experiments are just built so amazingly and so much more precise and whatnot. Okay, the MIT physicist Vicky Weisskopf dubbed such devices the Gothic cathedrals of the 20th century. 20th century. Some of it might have gotten started at the last part, at the end of the last century, at the end of the 20th century. I consider this to be sort of more of a 21st century thing, but whatever. From the start of construction to the completion of the first experiment, a decade can easily pass. This is in sharp contrast to the timescale of the processes being investigated, which occur in less than a billionth of a second. Such experiments repeatedly recreate and measure for a fraction of a second the conditions and interactions of matter and energy, including, as we shall see, the extremely rare events which may have been last experienced in our universe 10 billion years ago. 10 billion years ago. So once again, this is about 10 billion years now in the past versus what we were talking about in our first topic of this live earlier, which was going to be 5 or 10 billion years in the future. Okay, I just wanted to tell you about the 10 billion years from now into the future, as well as the 10 billion years from now, but into the past. Okay, I just love the future and the past on this same live stream. Okay, but as when I think about it again, some of the particle physics stuff is, of course, considered part of 20th century also, obviously, because so much of the particle physics discoveries, I mean, we didn't even discover, the proton or the neutron for a while. Those did happen in the 20th century. So particle physics is not just, is of course not a 21st century thing. It is coming from the 20th century. But when people ask about what's currently happening in physics right now, I would say the kind of fine tuning the experiments, building experiments, and making us have better measurements is a big part of that effort. Yeah. So I would say the later half of the 20th century until now, we have seen a lot kind of happen in these types of topics. But as a whole, the 20th century, especially in the beginning part of the 20th century, had so much excitement going on with, of course, special theory of relativity, general theory of relativity, photoelectric effect, the old quantum mechanics, and the quantum mechanics leading up to particle physics. So, and string theory. Let's not forget, we have also talked about string theory on these lives. You should definitely go back and check them if you're interested. From the start of construction to the completion of the first experiment, a decade can easily pass. This is in sharp contrast to the time scale of the processes being investigated, which occur in less than a billionth of a second. I mentioned that this is basically they're trying to recreate something that may have happened over 10 billion years ago. So sort of towards the beginning of the universe. The LEP collider imparted energies to elementary particles that were far beyond those produced anywhere else in our galaxy, except perhaps in the shock wave from an exploding star or in the final collapse of a gigantic black hole. Charged particles were accelerated by electric and magnetic fields around the tunnel so that they traversed the Swiss-French border without passports near the airport and then again at the base of the Jura Mountains 10,000 times each second. In the process, they achieved energies of almost 1 million times the energy they store at rest. Wow. Yet, these gargantuan values are still 1 million times smaller than the average energy carried by every particle when the universe was the size of a baseball. So the universe, of course, started very small, very compact, very hot, dense, energetic, and yeah. It was a very different universe, quite literally, back then. The collisions between individual particles at that time were so energetic that to recreate them with present technology, one would have to build particle accelerators with a circumference bigger than the circumference of the moon's orbit around the Earth. So it's very difficult, by the way. It's difficult enough to do this, but if you wanted even more energetic particles, then you would need the circumference of the colliders to be even bigger. And bigger than the moon's orbit around the Earth is quite impossible to achieve without getting very creative, I suppose. The voyage from LEP to the primordial universe is more than a voyage back in time. It is a voyage in scale that helps take us and our atoms much of the way from Brobdinging to Lilliput. As out of this world as the colossal detectors in the LEP experimental halls may seem, their mismatch to normal human scales is inconsequential compared to the degree to which the scales of activity in our current universe dwarf those that were relevant when atoms were conceived. Hi, Crazy Sick Wine. We're talking about atom. Can you rewind and see the first part of the live where we talked about our merger with Andromeda? The huge densities and temperatures at that time are reflected in an equally matched subatomic ferocity. Let us return to the barrage of atoms in a drop of water again, as seen under the microscope. The Brownian jumps of a dust speck are produced by the collective collisions of billions of jiggling atoms in the water, each momentarily traveling at hundreds of kilometers an hour. So, by the way, Brownian motion was also worked on by Einstein. Thank you. But a single subatomic elementary particle in the primordial gas, when the universe was the size of a baseball, carried enough energy to, in a single collision, knock the same dust speck not only right out of the water, but out of the Earth. Goodness, very extreme conditions back then, very. If we tried to ratchet up such a collision to a human scale, it would be like accelerating a rocket in space to such a high speed that upon colliding with the moon, it could kick it right out of the solar system. Of course, the moon would first actually break apart, as with a dust speck in the subatomic analog, but that is not the point. Gulliver never witnessed phenomena as foreign as this in all his travels. So this is quite foreign to us. How the universe was in the beginning is, of course, very foreign to us. We've come a very long way in the evolution of the universe to the point where we exist now. That is a very different universe than what it used to be when it first got started. Okay. So that's why it's difficult for us to not only imagine these things, but also to achieve these things technologically if we're trying to recreate some sort of conditions from the beginning part of the universe to kind of probe these physics of the subatomic particles. Not only did such incredibly energetic collisions occur in the early universe, they occurred often and everywhere. Remember that in a region the size of a single present-day atomic nucleus, there were then more than enough particles to comprise 1 billion nuclei. Moreover, the collision rate was so high that in 1 second, each particle in the early proto-universe would have been able to engage in more collisions than there are grains of sand on Earth. Do you see where this is quite different? But of course, 1 second is an eternity compared to the actual age of the universe at that time. Indeed, 1 second is far more than 1 trillion times longer when compared to the age of the universe at that time than the age of the universe is today when compared to 1 second. So the age of the universe is a lot bigger today, but when the universe is getting started, 1 second is a long time, right? So these are the conditions when the gist of our oxygen atom came to be, when nothing became something. How can I say nothing when there, in fact, was orders of magnitude more energy in a volume the size of a head of a pin at that time than is contained in our entire observable universe today? The point is, there was a lot of stuff, but not the right stuff. In spite of the mismatch between the mini world created momentarily during the collisions at CERN and the phenomenal collisions in the very early universe, they have one thing in common. In both, energy is directly converted into mass and vice versa. So we know about mass energy equivalence from special relativity, from special theory of relativity by Einstein. So of course this is possible. A striking example of the verity of Einstein's theory of relativity. When the universe was the size of a baseball, the energies involved in the collisions of pairs of particles were so great that 1 billion newly created particles could in principle spew out of the collision of just two colliding energetic electrons. And collisions were occurring so fast that no single particle preserved its identity for long. Electrons smashed together to make quarks, and quarks smashed together to make particles of radiation, photons, and all of these smashed together to make unknown particles that may last have existed in nature when the universe was less than a billionth of a second old. How can we make sense of such a mishmash? Thank you, Bing Top Marot. Thank you. This is precisely the problem faced by elementary particle physicists as they attempt to explore the fundamental laws of physics at accelerators. So the universe was really young, less than a second old, when this is what we're trying to probe in these colliders. And that's very difficult. Getting the conditions to be similar to that universe is very difficult. When we bang together two beams of particles in the LEP collider or in its higher energy cousin at Fermilab. By the way, Fermilab is in Chicago, if you've ever been in that area. So we create a host of new particles in each collision. Whenever whenever they're doing these collisions in these particle accelerator type of experiments, they create a lot of particles, even if momentarily. So anyway, these are particles created out of pure energy. Radiation converted to particles, radiation converted to matter, in other words. If not billions, then at least hundreds of new elementary particles are created as collision products. There may be 1 million collisions per second when the beams at Fermilab interact, each producing hundreds of particles. To simply record these events on disk would have exhausted the greatest supercomputers even a decade ago. In fact, one of the reasons that modern high-powered computer clusters were first tested at accelerator laboratories is that these were the first places that they were needed. It turns out that we could make sense of the resulting mess not by attempting to record every feature of the flotsam and jetsam, but by homing in on certain features deemed to be important. So they had to write down some stuff and they just had to leave out other things because they can't write so much information down. Lots and lots of information coming out of this particle accelerator type of experiments. In such a way, for example, we find that for every million incident protons that are smashed into a target amid the resulting menagerie of particles, we might find a single antiproton, the nucleus of the lightest atom of antimatter, antihydrogen. Antihydrogen. Wow. In such a way, for example, we find that for every million incident protons that are smashed into a target amid the resulting menagerie of particles, we might find a single antiproton, the nucleus of the lightest atom of antimatter, antihydrogen. Good night, says Stephen. Yes, I actually have to say good night as well. I'm going to read and go through the rest of this next time. We will start from the middle of this chapter 2 from the book The Atom Dr. Lawrence Krauss has written. And this is a very exciting chapter indeed, where we talk about matter and antimatter, and we just kind of got into it. So since it's kind of late, we will pick up from this next time. Thank you so much, everybody, indeed, for being here. See you next time, and hopefully you've enjoyed our discussion of the merger between Milky Way galaxy and Andromeda, and how the chance of that happening is kind of low, actually lower than we thought. And also this book, Atom by Dr. Lawrence Krauss, where we're talking about the early universe and some associated experiments and whatnot. And we will keep on discussing matter and antimatter next time. Thank you so much.